Let's look at a similar example. Let's look at the following question. What are all the solutions to cosine of x minus tangent of x minus secant of x equals 0 when 0 is less than or equal to x, which is less than 2 pi? So, before we start solving this, let's remember a few things. First of all, we can use the unit circle to our advantage. If we have everything written as sine of some angles equal to a number, we can solve that likewise with cosine. Another thing we can do is we can use algebra to decompose the equation into parts. And we have to check our domain. So since we have secant, which is 1 over cosine, we could possibly have the denominator as 0 for a potential solution while we're algebraically manipulating it. So we just need to make sure when we get all of our solutions, we just need to make sure that everything actually holds. So on another note, since we're talking about the unit circle, we want to use that. And there's 3 different trig functions floating around. It might be more beneficial just to write them using sines and cosines. So we know that tangent is sine over cosine and secant is 1 over cosine. So we should be able to at least reduce the number of trig functions floating around. Let's go to the board. Okay, so here's our trig function, or trig equation. Cosine of x minus tangent of x minus secant of x equals 0. And let's try to do what we talked about. We want to use the unit circle, so we need sines and cosines. There's no clear way to kind of pull this apart right off the bat, so that is a fail-safe. That if we don't know what to do, just write them all in terms of sines and cosines. So we have cosine of x. This tangent is really sine of x over cosine of x. And secant is really 1 over cosine of x. And then this is all equal to 0. So at the very least, though we have fractions introduced, we only have 2 trig functions. So that's pretty nice. What else can we do with this? Well, we can see that we can combine these as one fraction. This guy can't, because it doesn't have a denominator of cosine. So what we should do is actually introduce a denominator of cosine, since we already have to worry about it in our domain initially. So let's just divide this thing. Let's write it in a different color. We want to divide it by cosine of x and multiply it by cosine of x. Again, we're allowed to do it just to this term because we're really multiplying by 1. Cosine of x divided by cosine of x is just 1, so we're really multiplying this green cosine of x times 1. So let's do that, and since we have a common denominator, we can write this all as one monster fraction. So our denominator is cosine of x everywhere, and all that's left is cosine of x squared and sine of x and a 1. That's all equal to 0. So now we're reduced to a spot where we have a fraction is equal to 0. So what could we possibly do with that? Well, the only time a fraction is equal to 0 is when the top is equal to 0. If the denominator is equal to 0, this doesn't make sense, but the top equals 0 is all we need. It doesn't matter whether this is 2 or 4 or square root of something. This fraction will always be equal to 0 as long as the numerator is equal to 0. So just using fractions, we know that we have this situation. That cosine squared of x is equal to sine of x minus 1 equals 0. In that this has the same solutions as this, as long as cosine of x is not equal to 0. So what can we start doing now? This is much more difficult because we have sines and cosines, not just one. We can't factor one thing out. But what we can do is use the Pythagorean identity. So remember that the Pythagorean identity says that sine squared of anything, say theta, plus cosine squared of anything, so again say theta, of that same thing, is equal to 1. So why is this beneficial to us? Well, here we have this cosine. If we could switch this into a sine, then we'd have only sines, which is nice that we can use factoring. Alternatively, if we could switch sine to a cosine, then we could do the same thing here. And this Pythagorean identity is the main source of switching sines and cosines. So since we have a cosine squared and the Pythagorean identity uses cosine squared, we can use this identity to replace cosines with sines. And we can't just use it straight up. We need to manipulate this a bit. So we want to figure out what is cosine squared in terms of sine. So we just solve for cosine squared. So what do we have? Cosine squared of whatever's on the inside is equal to 1 minus this sine squared of theta. And in our case, we're not talking about theta, we're talking about x, so we can just switch this theta into an x. And so here we're going to use that pi, the Pythagorean identity that we just used over there. And we see that cosine squared is really just 1 minus sine squared of x. That's all this term right here. And then we have the remaining stuff. So this looks a little better. We've got just sines. That's our only trigonometric function. So we can actually start using this. So let's combine all of our coefficients so that we just have it simpler, so we can do like before and just treat this like a quadratic. So just as a reminder, we can think of this as some variable squared, and we can think of this as just the normal variable. So if we combine everything together, we get our a, our b, and our c from our quadratic formula, then we can factor this thing apart. So let's combine this. What is 1 minus 1? Well, that's 0. So all we have right now is just sine squared of x minus sine of x plus 0 equals 0. Well, it turns out this actually just worked out a lot nicer. We were going to have to use the quadratic formula prior or factor it, but here we have a little more simple factoring. We don't have to do the FOIL distributing type of factoring. We can just pull out common terms. So here we have two terms. They both have signs, so let's pull them out. So let's pull out the negative as well. So we pull out a negative sine of x. And what's left? Well, we got rid of this negative, and we have one sine left. And we're pulling out this negative sine of x. So what's left? Well, we really want to think that we're dividing by negative sine of x. So we really just have a positive 1. And that's all equal to 0. Whew. Okay. So let's keep messing with this. We've factored this into this term plus this, or times this term equals 0. So that means either this one is equal to 0, or this whole thing is equal to 0. So here I'll write with case 1. Case 1, negative sine of x is equal to 0. Well, that's the same as sine of x equals 0. And let's figure out what those values are. When is sine of x equal to 0? From 0 to 2 pi. Sine is the y-coordinate. So we are talking about height around here. And we want to go from 0 to 2 pi. So 0 is one solution, and pi is the other solution. And again, 2 pi doesn't count because we said this is strictly less than 2 pi. Therefore, our solutions for this guy are just 0 and pi. Now let's also look at 2, the second part. Either this left term was equal to 0 or the right term was equal to 0. So what was the right term? Well, it was just sine of x plus 1 equals 0. So this is the other option for how this whole thing can be satisfied. So let's solve for sine of x just like normal. So we subtract the 1 over and we have sine of x equals negative 1. And now let's find out what all our solutions are for this. What values of x from 0 to 2 pi, including 0, not including 2 pi, have output negative 1. So let's look at the unit circle again. Sine of x has got to be negative 1, so we're talking about a height of negative 1. So this is actually the only point right here. If we kind of move our hand all the way down, we have two solutions, two solutions, two solutions, and then all of a sudden we have 1. So this is our only possible solution. And what is that solution? It is 3 pi over 2. Okay. So it seems like these are our only solutions, and these are really our only possible solutions, our only potential ones. It could be less, maybe some of these don't make sense. So for this reason, we have to check the domain. So for this thing, we have that cosine could be anything. X there's no way that this doesn't make sense. And tangent is really sine over cosine, and likewise secant has a denominator of cosine as well. So we just have to make sure, our goal now is to make sure cosine of x is not equal to 0. Again, this is because we can't divide by 0. That doesn't make any sense. So cosine of 0 is actually 1, so that's okay. So this one is perfectly fine. Cosine of pi is -1, so that's perfectly fine. And let's figure out this other guy. X equals, so what's cosine of pi over, 3 pi over 2. And just for this one, let's look at the unit circle one more time. So we have cosine of, so the input, the argument is 3 pi over 2. So we're looking for an angle of 3 pi over 2. Here it is right here. And we're looking for cosine, so we're looking for the x-coordinate. Uh-oh, that's a 0. So we were specifically saying that cosine of x could not be 0. So cosine of 3 pi over 2 is 0, so that cannot be a solution. So actually, our solutions to the above equation are only x equals 0 or pi.